Morning, everyone. This is Sundaratre, and we are looking at the second lecture in the series of process selection considerations in Module 4 for ME 575 Design to Manufacture Digital Tool. And we'll build off from the conversation in the previous lecture where we look into some more details of cost estimates, since an objective of minimizing cost was repeatedly seen through the previous three modules. So, how do we actually deliver on it? So, if you recap, there is a process universe, and within that are data sets for various families of manufacturing processes. And within each processing class, such as shaping, you have many different alternatives ranging from casting, powder metallurgy, so on. The member in molding has variations like such as injection molding, blow molding, compression molding, and there are certain attributes that go into um, what is possible as a constraint imposed upon by the choice of manufacturing process in terms of not only the geometrical limits that can be made, but the economic batch size. And this is a consideration that we will take into account during the course of today. Towards the end of last class, we had looked at the fact that computing the cost of a product would depend upon many contributors, ranging from the raw material, the manufacturing process itself, and any post processing that is required. And the specific contributors in each category could, in competition, at, for any given material, right? Materials might perform better from a cost basis um, in one of these categories, but worse in the other. And so the aggregate of that cost is what we are looking at in terms of the overall cost considerations. We took an example of a door panel last class, and one of the indications that we saw was this: when you map part cost versus batch size, it can turn out that a combination of material and process for smaller batch sizes in this particular case, right? These are the trends. Steel fabricated by roll pressing was the better alternative for small quantities for the door panel compared to the thermoplastic that was molded. But as you went to higher and higher manufacturing batch sizes, there was a crossover at which point the molded thermoplastic turned out to be a better choice. So, how are these processes evaluated in terms of their cost performance? So, we had looked at the fact that the cost might be one, but what you can sell it for really depends upon the perceived value um, by the customer, how much you can charge to be able to work it out. And so, the cost itself is only one part of the equation. Is there enough demand for it? And then at what price point is that demand sustainable? These are some things that need to be input into the cost model for selecting the material, the process, the shape, and so on, in order to minimize the cost as an objective function. Let's look at how this model is put together and how it is implemented so that we can then understand what are the drivers for cost, go from there, right? So we have this cost, price, value competitors. Let us put this in context in terms of the fact that the price is somewhere in between the cost and the value for a profitable business. The closer P is to V in value, the greater are the chances that you'll have a profitable business. You don't want P to be less than C, at which point you're better off not continuing with that product. So, some common notations in terms of not worth the price means that P is greater than V, and so that's a big. Good value for money means P is less than V, and so you're so far so good. But just because they see the value doesn't mean they're going to buy it, right? And they're going to buy enough of it, or that you can make it in a reliable manner. So, with these considerations, let's look at the cost of manufacture and the material cost going into the cost for producing a product or a component within a product. Immediately, we run into a particular set of unknowns and uncertainty and risk because, as you can see, this is historic data, and if you continue it to today, the same thing occurs. You can have wildly fluctuating prices for materials, right? It's a factor of 3 over here in the top for copper. Another example is nickel, which is both of these are common alloying agent in steels. So even though these are specific to the two materials, if they are introduced into other alloys, their costs are going to go up as well. Here's a factor of 4 difference, right? If you have such wildly fluctuating costs, what happens, right? And why do these things fluctuate, do you think? Think about it, right? These all come from some place or the other because of geographic factors, because of maybe political conflicts, maybe the pandemic, maybe disruption of supply chains. These kinds of costs are going to go up because of the competition between demand and supply. So this is something to consider. In addition, there are certain types of materials that, for instance, the rare earth materials that go into magnets, for instance, and the batteries, they are only produced in a few, are available in a few countries across the globe. And so correspondingly, when supply is short, prices can go up a lot if the demand goes up suddenly, as in the case for batteries for electrical vehicles. Cost modeling for material selection will start out with a fixed cost, but note that the analysis can get more involved when you begin to take into account uncertainty in the actual input variables or the reliability of those input variables, which is the case for all types of modeling.